Have you ever wondered what makes a problem solvable by a computer? Well, you're not alone. This question has fascinated computer scientists for decades and has led to the concept of decidability. Decidability in the realm of automata theory and formal languages is the property that determines whether a problem has a definitive answer, given a set of rules or constraints. It's like a detective story where the detective, in this case, a computer, is trying to find the culprit, the solution, within the rules of the game, the algorithm. Now you might be thinking, what exactly is an algorithm? Well, an algorithm is like a recipe. It's a set of instructions that a computer follows to solve a problem or reach a goal. And a Turing machine, that's a mathematical model of computation that defines an abstract machine, which manipulates symbols on a strip of tape according to a table of rules. So when we talk about decidability, we're asking whether there's an algorithm or Turing machine that can always halt and correctly determine the answer to a problem. If such an algorithm exists, the problem is termed decidable or computable. It's like having a recipe that guarantees you'll bake a perfect cake every time. On the other hand, if no such algorithm exists, the problem is said to be undecidable. These are the problems that represent the fundamental limitations in computation, the recipes that no matter how we tweak them, we can't guarantee a perfect cake. One of the most famous examples of an undecidable problem is the halting problem, posed by Alan Turing in 1936. But we'll dive into that a little later. Decidability is a central concept in computer science. It helps us understand the computational capabilities of various models of computation, like finite automata, Turing machines, and formal grammars. It allows us to delineate the boundaries of what is computationally feasible and what lies beyond the reach of algorithms. So, decidability is about whether there's an algorithm that can always provide the correct answer. But remember, the world of decidability is full of mysteries and complexities, and we're just getting started. Now let's delve deeper into what we mean by decidable and undecidable problems. Decidable problems in the realm of theoretical computer science are those that have a definite yes or no answer. They are the problems for which there exists an algorithm or a Turing machine that can always halt and provide the correct answer for any given input. For example, the question, does a given string belong to a certain regular language, is a decidable problem. This is because we can construct a finite automaton for the language and run the string through it. If the automaton accepts the string, the answer is yes. If it rejects the string, the answer is no. Hence, this problem is decidable. On the flip side, we have undecidable problems. These are the problems for which no algorithm can provide the correct answer for all possible inputs. That is, these are problems that are inherently unsolvable. A classic example of an undecidable problem is the halting problem. This problem asks, given a description of a program and a finite input, will the program eventually halt when run with that input? Alan Turing proved that there is no algorithm that can solve this problem for all possible program input pairs. Hence, the halting problem is undecidable. It's fascinating, isn't it? The world of theoretical computer science is filled with these kinds of problems. Some are solvable, some are not. Some problems are like well-trodden paths, where we know exactly where to go and what to do. These are our decidable problems. Other problems, however, are like uncharted territories, where no matter what we do, we can't find a universal solution. These are our undecidable problems. So, to sum up, if there's an algorithm that can always halt and provide the correct answer, the problem is decidable. If not, it's undecidable. It's as simple and as complex as that. But don't worry, we'll continue to explore these concepts in the next scenes. Our journey into the fascinating world of decidability and undecidability is just getting started. Remember, if there's an algorithm that can always halt and provide the correct answer, the problem is decidable. If not, it's undecidable. One of the most famous undecidable problems is the halting problem. This problem, proposed by Alan Turing in the 1930s, is a real brain teaser. It asks whether a given Turing machine, a theoretical device that manipulates symbols on a strip of tape according to a table of rules, will halt or stop on a particular input. Imagine you've written a program. It's running, doing its thing, but will it ever stop? Or will it run forever, caught in an infinite loop? That's what the halting problem wants to know. Now you might think, well, I'll just wait and see. If it stops, it halts. If it doesn't, it doesn't. But here's the catch. You can't wait forever, and that's where the halting problem becomes undecidable. Alan Turing proved this with a clever argument. He assumed that there was a Turing machine, let's call it H, that could decide the halting problem. You feed H any Turing machine and input, and H would tell you whether it halts or not. Sounds good, right? But then Turing introduced a twist. A new Turing machine, let's call it T. This machine takes an input, runs H on that input, and then does the opposite. If H says the machine halts, T runs forever. If H says the machine runs forever, T halts. Then Turing asked, what happens when we run T on itself? If T halts, then by its own rule, it must run forever. But if it runs forever, then it must halt. This contradiction means that our original assumption that H, a machine that decides the halting problem, exists, must be incorrect. And so, Turing showed that the halting problem is undecidable. There's no algorithm that can determine, for all possible programs and inputs, whether a program will halt or run forever. So, next time you're waiting for a program to finish, spare a thought for the halting problem. It's proof that some problems, no matter how simple they seem, are beyond the reach of computation. And that's the halting problem, a classic example of an undecidable problem. Another important concept in decidability is Rice's theorem. Named after Henry Gordon Rice, this theorem is a cornerstone of computability theory. Rice's theorem asserts that every non-trivial property of partial functions is undecidable. Now, you might be wondering what we mean by non-trivial properties. Simply put, a property is non-trivial if it is not true for every Turing machine, or false for every Turing machine. In other words, if there's some variation between Turing machines regarding this property, then it's non-trivial. Let's break it down. If we have a property that is true for some Turing machines and false for others, then, according to Rice's theorem, there's no algorithm that can decide whether a given Turing machine has that property. This means that we can't create an algorithm that will always correctly determine if a Turing machine has this non-trivial property, no matter how we structure the input. This is a profound revelation. It tells us that there are inherent limitations to what we can compute. There are simply some questions about the behavior of Turing machines that we can't answer using algorithms. This doesn't mean that we can't make any determinations about Turing machines. We can still analyze and understand specific cases, but Rice's theorem underscores the fact that we can't make blanket determinations about all Turing machines. So what are the implications of Rice's theorem for decidability? Well, it puts a hard limit on the types of questions we can answer about Turing machines. It tells us that any attempt to solve a non-trivial problem about the behavior of all Turing machines is doomed to failure. We can't find an algorithm that will always give us a correct yes or no answer. Rice's theorem is a humbling reminder of the boundaries of computation. It tells us that there are limits to what we can know and predict, even in a field as precise and rule-bound as computer science. So Rice's theorem tells us that non-trivial properties of Turing machines are undecidable. Decidability also has interesting applications in the study of formal languages and automata. It helps to delineate the closure properties of different classes of languages and automata. For instance, regular languages, those that can be expressed with a finite state machine, are decidable. This means we have an algorithm that can determine whether a string is in a regular language or not. Similarly, context-free languages, those that can be passed by a push-down automaton, are also decidable. We can always find an algorithm that decides whether a string belongs to a context-free language. On the other hand, we have recursively enumerable languages, which are semi-decidable or recognizable. An algorithm can confirm if a string belongs to such a language, but it might run indefinitely if the string does not. Non-context-free languages and non-recursive languages, however, are undecidable. There's no algorithm that can conclusively determine membership for every string. These closure properties help us understand the computational capabilities of different models of computation. So, why is decidability so important in computer science? Decidability acts like a compass in the vast world of theoretical computer science. It helps us pinpoint what is computationally feasible and what's not. Imagine you're working on a problem. With decidability, you can determine if there's a path, an algorithm, that will always lead you to the correct answer. And if there's no such path, decidability will inform you, saving you from a futile expedition. In the context of automata theory and computational complexity theory, decidability provides a framework to understand the inherent limitations of computation. It's like a map that outlines the territories we can explore with our current computational capabilities. Understanding decidability is like unlocking a deeper understanding of the nature of computation itself. Decidability is not just a theoretical concept, it's a practical tool, a guiding light in the ever-evolving landscape of computer science. And that's a wrap on decidability, a key concept that helps us understand the limits of computation,